Hello, everyone. Welcome to my talk. I'm TK Chen, a postdoc in University, working with Tom and Alexandru. Today, I'm going to tell you how we simulate ionization front propagation during reionization using smooth particle radiation hydrodynamic that we have been recently developed in Swift. The method paper has been accepted, and you can find it on arXiv, and we are also preparing the physics paper about the propagation of ionization front. Reionization is an epic episode of the universe. However, there is a lot of uncertainty. First of all, what is the sources of the reionization photon? And also, how the ionization photon escape from galaxies. Second main uncertainty are what is the strength of the photon? Can the inhomogeneous intergalactic medium, for example, Minihalos and Ionization systems, significantly increase the photon budget? This also have an implication on the mean free path of ionization photon. For example, recent observations find that the mean free path changes suddenly during the reionization. Then, why inhomogeneous intergalactic medium will affect the photon budget? It's because of recombination. When an ionization radiation ionizes an hydrogen atom, the electron will get kicked out. However, an electron can also come back to an ionized atom, and so such that you need an extra photon to ionize this hydrogen atom. So that means if there's more recombination, then we need more photon to ionize the universe. Unfortunately, the recombination rate is proportional to the square of the ionized gas density. We can also define a factor called clumping factor to quantify this effect. It basically is a mean of the square of the ionized gas density. So if the medium is more clumpy, then you need extra photon consumption. Previous theoretical simulations show that the clumping factor can be larger than 10, so it could be a significant budget to add to the reionization. In order to understand that, we also need to understand the Minihalos. 20 years ago, Heyman, in his theoretical work, found that the total number of recombination photons can increase by a large factor because of the presence of Minihalo, which is a very small dark matter halo that increases the photon budget. The minimum Minihalo mass is around 10 to the 4 in solar mass. So in order to understand that, we need a dark matter mass resolution to be below 100 in solar mass. However, there's another important process, is the evaporation of Minihalo. Because the ionization will also heat up the gas to 10 to the 4 Kelvin. So when the ionization runs through the Minihalo, it heats up the gas, and then the gas will get expanded. And after 150 million years, then the Minihalo will eventually get evaporated. These have been demonstrated by 2D simulation by Shapiro, 2004. So this means in order to understand the Minihalo evaporation, we also need radiation hydrodynamics. So there are also computational challenges in order to understand the reionization on the IGM. First of all, we need large enough box size to sample large-scale structure. We'll need high mass resolution to resolve the very small Minihalo. Finally, because we don't quite understand what is the sources of the reionization, so we need multiple intensity of the UV radiation. Finally, we also need on-the-fly radiation hydrodynamics to understand the evaporations of the Minihalo. However, we already developed the SPX71LT. We can do all of these with the newly developed schemes. The SPX71LT is a newly developed radiation hydrodynamical method, which is a combination of a two-movement radiation transfer method with the smooth particle hydrodynamics, which is improvement on SWIFT, a task-based parallelization galaxy simulation code. The method paper has been accepted and you can find it on arXiv. This method is quite similar to hydrodynamics. That basically you have a mass or energy equations and also a flux equations. You have an analog equation for the radiations. So basically treating the radiation as a fluid. In order to close the movement hierarchy, we postulate that the anisotropic pressure tensor P over there can be closed by using a local M1 closure, which is a local closure only depending on the local gas property so that it can be easy to parallelize. The abstract M1 method have a lot of advantages. First of all, it's straightforward to implement in any hydrodynamic code because the equations are quite similar. Second, it's adaptive. It's the same as the SPX equation, so it has the same particle resolution as SPX. And then it is very efficient. Computational cost is independent of the number of sources, and we can use reduced speed of light approximation to accelerate it. Finally, it's accurate in the optically thin and optically thick limits. Our code also performs really well in multiple tests. For example, in the field propagation test on the right, that we find the radiation does follow the speed of light and maintain its directions. And then in the middle, that we find the X2 region matches the analytic solutions. And finally, on the bottom right, that you find the shadowing also perform really well, which is very important for the Minihalos evaporation test. Here, we introduce a simulation SWIFT that we show we have multiple redshift and also intensity at a large enough boxes and high enough resolutions. We propagate two ionization fronts from opposite sides of the box, and then we adopt on the right radiation hydrodynamic with reduced speed of light approximations, and we capture the ionization front propagations and also the photon consumptions at different times. This is the cartoon picture that we are showing what we would expect from those simulations. That we will see the Minihalos relaxations, we will see the evaporation process and the ionization of the IGMs. Here is the movies of one of the simulation box. On the right, on the left, we show the neutral fractions. That basically the ionization front ionizing the IGM. And then during the ionization, it also heating up the temperature so that you can see the temperature is going up to 10 to the 4 Kelvin. And the density will eventually get more smoother. The reason is due to the heating of the gas. In order to understand better how the ionization front affects the small scale structure, we compare the realistic intergalactic medium and also a uniform intergalactic medium on the right. We use the same photon intensity and then try to inject the radiation from the side using the same intensity. And then you find that there's a very significant difference is that in the realistic intergalactic medium, the mean ionization front actually propagates much faster, and the dense gas trap the ionization front. However, in the uniform one, the ionization front is very sharp and is very uniform. We can understand the difference by looking at the gas distributions of the IGM. Actually, we find that the more probable gas distribution, the gas density, is lower than the mean IGM density by half. So basically mean that in most of the gas, actually, the ionization front propagate 2 times faster. We can quantify this by checking the ion distance, which is the distance from the boundary epoch to the 15% ionized position. We show the time evolutions of the ion distance on the right. The blue dashed line shows the uniform ionization case, and then the realistic IGM that we show in the red line. Not only we find that the realistic ionization front position move faster a little bit, it also have a much bigger scatter due to the inhomogeneous IGM density. In the future, we want to understand this using analytic models. Okay, here we return to the IGM clumping, looking at the time evolutions of the clumping factor. We find that the clumping factor does increase significantly during first 10 million years due to the rapid ionization, and also the gas does not have time to respond. However, after tens of million years, the gas start getting evaporating and relaxing due to the photoheating. So the clumping factor slowly going down. After 300 million years, almost all the Minihalos get evaporated so that it returns to a very low value, around 2 to 1. Another interesting quantity to look at is the number of recombination per hydrogen atoms. We are showing you that at different redshift and different intensity, the high photoionization intensity is shown in the upper left, and the low photoionization intensity is shown in the lower right. We find that regardless of the intensity, the recombination still is important. Around 10 to the 40% of the photo consumption is due to recombinations. If the photoionization intensity is lower, then the recombination rate is also lower. However, the recombination still increases after 100 million years. The conclusion is we have developed a new efficient and adaptive radiation hydrodynamics method in SWIFT, SPXM1LT. We use that to simulate ionization front in a 1 megaparsec box. We can resolve Minihalos, and then we check the ion and then find that the ion propagate faster than a uniform IGM. And then the photo evaporation can reduce the IGM clumping factor. However, still 10% to 40% of extra photon consumptions is due to recombinations of the clumpy IGM. We are still doing extra works, for example, developing an analytical model for the ion propagations, calculating the mean free paths, and studying the impact of ionization fronts on Minihalos. We also have some future work that related to the SPXM1LT, mainly working with Alex and Leiden. First of all, we want to develop a multi-frequency rate transfer. Currently, we have the hydrogen and helium ionization photons. Second is to have a radiation hydrodynamics in interstellar medium with non-equilibrium chemistry and compare with observations. We also want to make a bigger simulation, so we require subcycling and task-based parallelization scheme in SWIFT. And finally, we will make the radiation transfer module public on SWIFT website so that other people can use it. Thank you everyone for coming.